Thank you.
Yay.
All right, for coming. You're welcome to scooch more in if you want. I really want this to be a conversation, and I think you too, right? Okay, so I'm Allison from Foresight Institute. I think I know almost all of you here. And Foresight Institute is an institute that's focused on technology as a fundamental importance for the human future. And Lou will say a few words at the end about how to best get involved with us if you want to. But just for now, if you want an update on those events in the future, then join the mailing list at Foresight at bit.ly/Foresight list to stay up to date. This one sold out in like under an hour, and I think it's been more and more crazy with the salon. So sign up if you want. Okay, so this year we focused our salons on the topic of strengthening civilization, and this salon tonight on the Dissolving the Fermi Paradox and the far future is part of the Salon Series on strengthening civilization. And in that series we tackle one part of civilization per month, and we started out with strengthening human biology and morality, and we had David Eagleman and Arvind Gupta to do that with. We then focused on creating effective counterculture with Jun Yoon, and on our hidden social motives with Robin Hansen, and then on coordination with Peter Egglesby, Alyssa, who's here, Paul Cristiano, and Christine Peterson, and then looked at the history of civilization with Samuel Burja just last month, a couple of weeks ago. So I think tonight we can take it out and really dial it up a notch, and not only talk about the history, but about the future of civilization or of even interstellar civilizations. And I'm really, really glad to be doing that with Anders tonight. Anders Sandberg is from the Future of Humanity Institute, and he's known and appreciated by many in this community. And he's written and talked in breadth and depth, both extensively about everything from personal cognitive enhancement to space races and the far future as a whole. So there's really a lot to cover, and we'll barely scratch the surface, but it can serve as a nice introduction. I very much encourage you to delve into his readings, and we had a little meeting last Wednesday on the books we are both writing on the far future. So I'd love for this to tackle first the paper on Dissolving the Fermi Paradox, which I think why you're all here, then the book on the far future generally, and perhaps talk about a few papers of yours as well. And because those salons are kind of always a mouthful, I made a little outline, and I'm sure we will digress naturally, but I would love to start with the Fermi Paradox paper first, then talk about the nature of the far future, then about interspecies ethics in the far future, then about interstellar coordination and space races, then the roadblocks that are on the way to get there, something like AI, and then how we get from here to there. So what can we as humans do to get there?
So not much to cover. So not much to get through.
No, not much at all.
Is that the whole book, or is that just today?
Just tonight. I mean, as I said, this is only might be on our plate. We might get stuck on the first topic, and that's fine too, because the first topic is Dissolving the Fermi Paradox. So let's start perhaps with a quick poll. Who has read the paper, or at least watched or listened to the 80K podcast that I sent out? Okay, that's a couple.
Yeah.
Maybe, and this is also a very good question. Do you want to get us up to speed on the paper? So what is this paper stating?
So the Fermi paradox, or rather the Fermi question, when Enrico Fermi exclaimed during lunch at Los Alamos in the 50s, "Where is everybody?" is really based on this assumption that there is a tension going on. You say that you have a paradox when you have some theory that contradicts some fact or some other theory that you really believe in. And the implicit theory going on here is that the universe is really large, really old, and there should be some decent probability of getting intelligence. Hence, there should be a lot of intelligence around. We don't see that. Something is wrong. Now, there is a fair number of people, of course, said, oh, it's obvious. There are no aliens around. The probability is really low. And they typically then tend to leave the debate. But there is also a lot of people who are trying to come up with explanations. I have been among them. I have another paper that I find at least very amusing called the Estivation Hypothesis that argues that maybe there are aliens around, but we're all sleeping because it's too hot. In a few trillion years, it's going to be a balmy 10 to the minus 29 degrees above absolute zero. And at that
and have harvest time, and now we can start working because it's kind of a crisp autumn of the universe. I don't believe this is actually the explanation of an empty sky, but it's going to tie into some of the other stuff with this guy. But people have been coming up with various explanations, and many people feel that this is a real problem. The reason I got interested is that we're interested at the Future Humanity Institute in the future of humanity, not necessarily the aliens, but if the explanation for the Fermi paradox is that civilizations don't last very long, then the empty sky is a really important piece of evidence that we ought to do something about or try to figure out how to react to. Except that, of course, that knowledge didn't help the aliens in that case, so there is a real problem. Now, when people generally deal with the Fermi paradox, we used in our paper the Drake equation, which many of you are familiar with, where you just multiply together a number of factors to get a guesstimate of how many civilizations there are in the Milky Way. Now, this is intended as a way of organizing our lack of knowledge. It's not exactly intended as a tool for actually making an estimate, although a fair number of people do that and use that as a motivation, for example, for why we should be listening through radio telescopes. Some of these factors we understand really well, like how many stars are being formed in the Milky Way per year. We were a bit uncertain back in the 60s, but it turns out that Carl Sagan's guess was kind of spot on already. So that works out really well. Then you have the middle factors, which are like, what's the fraction of Earth-like planets that get life? We're uncertain about that. What about the fraction of life-bearing planets that get intelligence? We're really uncertain about that. And then you have the final factors. Well, what fraction of civilizations do communicate or do stuff we can notice, and how long do they last? We're uncertain about that. But normally how this gets used is in a slightly sloppy sense. People talk about it, they gleefully tell the reader that we know that practically all stars have planets, so that factor is not very uncertain, and then they get to the life factor. And at this point, many authors say something like, we're super uncertain, and let's make this guesstimate. And admit that we made up this as a guesstimate and that it's super uncertain, and then we go on, and in the end, we get a number. They multiply together these guesstimates, and they say, of course, this is really, really uncertain because there are some numbers in there that we really don't know. But you do get a number, and it's kind of a suspicious tendency for either to get one, for people who are somewhat pessimistic, saying we're the only ones in the Milky Way, or getting about as many civilizations as the number of years we tend to survive, which typically means that we have millions or at least hundreds of space brothers out there, so we should really be watching the skies. Now, even if you believe that there is about one civilization per Milky Way, actually that puts, I think, about 40% that we actually get somebody else in the galaxy. So that's already a significant guess. But notice what something weird happened here. We took an uncertainty, but an uncertainty have a range. I can be very uncertain about something or not very uncertain. But here we just turn them into point estimates, numbers that we multiply together. And this is where things get weird, because that can create a very strong bias. So you can imagine a toy example that we have a number of factors that are between, let's say, 0 and 0.1. And then I multiply together 9 of them. So that would be in 0.05 to the 9th power. So I get some kind of expectation if I take the point estimates. And I would say, yeah, it's really unlikely given this expectation that we're alone in the galaxy. But if we actually do this properly with uncertainty intervals and carefully calculate the probability distribution, we actually get a very big probability that we're alone, because some of the factors might be really low. So you get a bias here where you kind of ignore this big tail possibility. And this is what we are arguing has gone wrong in a lot of this reasoning. Of course, a lot of people have been trying to get good numbers, which is hard, but by not actually modeling the uncertainty, you get a bias. And we have confused a lot of people by reviewing people's guesstimates from the literature and kind of just taking the different authors' estimates and just randomly combining them to kind of get a joint view of what people are saying. And that already produces this distribution with a long tail towards low probabilities. So even if we take the optimists who write papers about this, not the pessimist who thinks this is foolish in the first place, even the optimists kind of implicitly imply that, without knowing it, that there actually is a fair probability that we're alone. Now, that is probably a very biased sample. A lot of people just copied the numbers from Carl Sagan's papers, for example. He's kind of suspicious of similar many guesstimates are to his guesstimates. I think they're pretty decent, but it's still very clear that we're being copied. So you can also try to model a real scientific uncertainty. And this is where it actually looks like the uncertainty range could be much bigger, many more orders of magnitude in the probability of life. We really don't know whether life is super easy or super hard. It could be that actually give a puddle some organic chemicals and wait for a month and you actually do get spontaneous life. We haven't seen it in the lab, but maybe we haven't looked very carefully for it. And it always gets out-competed by some bacterium that is way more advanced than this. It could also be that, yeah, it actually does require one of these crazy combinatorial things that creationists like to bring up. We actually had to be careful when writing this paper, so creationists couldn't quote mine it. It's an interesting problem. So we end up thinking that we actually get a very broad uncertainty, at least 100 orders of magnitude. I know Aubrey might disagree with me on this, but it's an interesting question how to characterize this. Yes, exactly. But even if we can say, okay, let's say just 20 orders of magnitude, the argument still works. Because basically what happens is you get this tail and a fairly high chunk of probability that we're alone in the Milky Way and the observable universe. That doesn't mean we actually are. It's just that given our knowledge, it looks like an empty sky shouldn't surprise us too much. It's not a weird thing. It's not, and it turns out then it's not strong evidence that we're doomed, which is very good news. We can try to update this also by saying I haven't seen any misparked UFOs on my way here. So that can update. So we are not living in the Star Wars galaxy where you kind of weird aliens in every bar. So we can cut off the most optimistic one. Then you get a little bit of an update of the parameters. And it's the most uncertain one that gets updated the most. So again, it seems like we're really uncertain about our future, but not as uncertain actually, I think, as the probability of life. So again, we get this reason to think that the stars are not foretelling our doom. Of course, past performance is no guarantee of future performance, so we humans can totally doom ourselves, but that's our own fault, and we better fix that on our own. We can't really blame the universe for that. Sorry, that could turn into a little mini lecture, but yeah.
Yeah, I think like one thing that I thought was striking after reading it was not that there isn't another filter ahead of us, but the only thing I think that we can say is that we might have more responsibilities than we thought before.
Yeah. So if we are really very alone, it might feel a bit lonely, but we got each other, and we have an entire universe to do something good with. Now, if we're not alone, of course, we need to get along with the neighbors, assuming that we can get to them.
Or they can get to us.
No,
Yes. Yeah.
All right, you want me to heckle?
Yes, sure, go for it.
All right, so first I'm going to anti-heckle. I'm going to say how much I love this paper.
Oh, thank you.
Because the fact is, you know, I've obviously been aware of the Fermi Paradox for decades, but it had never even occurred to me that we were making this fundamental mistake that you guys have highlighted, that we're just multiplying probabilities in an overly simplistic way. And I think it takes the debate hugely forward, just in one big step. So that's fantastic. And I really want to, congratulate the three of you for doing this. However, as soon as I read it and started to think that way, the way that you have encouraged us to think, it occurred to me that maybe one needs to take the next step that actually may take the conclusion back in the opposite direction and kind of, what's the word? Condense the paradox, right? Sediment, I guess. So the big problem is that if we look at the steps in your argument, as you say, some of the steps, the range of uncertainty is really quite narrow, so we can kind of like lose them really, where they're kind of done, right? And so I was interested in the ones that were the widest. And the thing I thought that you didn't take into account, that needs to be taken into account, is what I'm thinking of as known unknowns, or at least highly likely unknowns. Which means, essentially, looking at the rate over the recent past, let's say the past century, at which we have made discoveries in the space in question that we couldn't have anticipated because they were really just new ideas or accidental or whatever, but that have improved the lower bound on the probability in question. And the particular ones that I'm looking at are the ones in the middle of the Drake equation, the ones that have to do with getting basically from chemistry to biology, right? So whenever one comes across a new missing link, suddenly the lower bound goes up. I mean, often quite a lot, right? You've got more steps, essentially more components in the new Drake equation, but each step has a better probability, and so you end up with a better product, even if you do it right, the way you did it. So I'm thinking, well, we need to look at the history, the rate at which we are making these discoveries, and we need to ask ourselves, is that rate slowing down? Does it look as though we're hitting an asymptote, a diminishing returns thing? If it doesn't, then we can predict with reasonable confidence that there's more missing links to come, and therefore that the probability is going to the lower bounds of these probabilities are going to rise, and therefore the Fermi paradox is going to re-emerge. That's my essence of it.
Thank you so much for that. I think this makes a very important point. These bounds and this uncertainty are about knowledge. It's not like I actually have access to the simulation where the universe is running on and they can see what the probability distribution is. We don't know that, or that it is a simulation for that matter. But we have a certain range of knowledge, and we know that has shifted. In fact, there is a very good book on the Drake equation by Vacco that has chapters for the different parameters and how people have been updating them. And some of them have been going back and forth in very interesting historical ways.
Sorry, I should tell you, you're still doing that four-syllable thing. Parameter.
Parameter, yes.
Let me explain. So one day, about 15 years ago, Anders went on stage and he said hyperbole. And after a bit of conversation, it turned out that the reason for this is that he learnt English from Scientific American, and that in Swedish it is extraordinarily rare for words not to have an emphasis on their first syllable. Whereas it turns out that in English, four-syllable words have an emphasis on their second syllable quite a lot. And this is...
Yes. In any case, not to get hyperbolic about it, but so one of the interesting things here is that some people have been asking me, so is this paper indicating that we should just stop looking for aliens? And my response is no, the kind of opposite. We should actually try to use this to look at where can we do the most good here. And one of the things is, of course, where life comes from. Figuring out more about that will tell us quite a bit and reduce the uncertainty. And we might, of course, end up actually realizing, we actually now believe that we have a real Fermi paradox because now we managed to bring down the uncertainty. That can happen. It could happen that we discover ruins on Mars tomorrow. That definitely changes the probability distribution a fair bit, probably in a mildly scary direction. So there are updates that can do this. And we can also start thinking about where can we do something useful. So I tell the astrobiologists that they are doing important things to get the life probabilities. And especially where we to find life in space. It would be very interesting to see, is it based on the same kind of DNA as ours? So in the solar system we might suspect that there is some panspermia going on, that bacteria and spores are spread between planets by meteor impact. Or maybe it's independently evolved. If it's independently evolved, the life must be way more common because you got it several times in the same solar system. If you have a panspermia, at least our solar system is thriving and it's probably leaking a bit of spores to others. So it goes up, but not as strongly. So we can do very useful things there. I'm a bit more pessimistic about the communication factor and the longevity factor. That's kind of part of our other research. But I do think that we actually have a reason here to start digging in and trying to see what we can fix the factors with.
I think we'll shed some light on this in the near term with these big telescopes that are being built to look at atmospheres of other planets, because the oxygen content here is largely thought to be most likely because of the life certainly I think that those sort of theories plus our observations might constrain that
Oh,
particular
yeah.
factor quite quickly, like within the next decade.
Yeah.
But
So-
then the intelligence one seems to be the one that would then be the biggest
Yeah.
unknown thereafter. Do you agree with that?
I agree, and it's kind of annoying to have two big factors. If there was just one really big factor that we could push down, then the uncertainty would decrease quite a bit. And the tricky thing about the intelligence factor is that it might have more to do with genetics than brains. So I used to think that intelligence can't be that hard. After all, there's a lot of creatures on this planet with fairly big nervous systems that are not super closely related to us. So of course you might say, yeah, but it took a few billion years from life emerging to nervous systems that started writing papers about nervous systems. So, but still, it looked pretty okay. But then Eric Drexler pointed out that there is another factor that's important. That is, our genetic code is pretty good for evolving. It's kind of sloppy enough that you get mutations, but it's also resilient enough so it doesn't just melt down. But you could imagine a slightly more brittle code that's good for replication, but doesn't mutate that well. So having a mutation rate that's a tenth of the one we see on average in the biosphere doesn't seem totally crazy to have. And you can certainly invent other coding systems that could be way more rigid. And that would suggest that, well, that planet that had that slightly less mutating system, well, it would take 40 billion years to get to brains, at which point, of course, most suns would have burned out. So there might be that we have at least two kinds of life. We are the kind of A life, the life that evolves fairly quickly into complex stuff. But we could be B life, that is fairly bad at evolving quickly. Now, if B life is easier to get, a kind of low-hanging fruit, the early biogenesis is trying various things, and it hits on a coding system, it might be that B life coding systems are easier to get to than A life. We might be a fluke, one of the really rare ones. And that might mean that there is a lot of life out there, but most of it is kind of prokaryotic stuff.
And the initial conditions of the bay prevent it to yeah.
Yeah, so this is again something where we need another way of checking, and I think this is where we might go to the people in the lab and try to have them make weird coding systems instead of trying to see how quickly could you make different kinds of code.
Yeah, A-life, not to be confused with artificial life.
No, yeah.
Okay, yeah.
Okay, so I have many points I'd like to raise.
Okay, start with one.
Well, I think that I'm going to just touch on one thing and then say it again. I think that we're going to realize, first of all, your paper is wonderful in the sense that it's one of these papers that you read it and you go like, well, that's obvious in retrospect.
Yeah.
So that's the mark of a great paper. That's something that doesn't come along for 40 years, but it's obvious in retrospect, okay? The second thing is that I think we're going to find that there are a lot of other factors that we've kind of lumped together, and we're going to want to tease them apart. One thing I'd just like to mention along those lines is, well, there's the unicellular to multicellular transition. There's all these transitions. There's the idea that the dinosaurs were running, they were the dominant macro form for 200 million years, and then this impact had to happen to stir things up. So there's that whole part of the equation of they were in a way B life. Maybe not, they were the nervous systems, but
Lowercase A life.
They were lowercase A life, right? And then the main thing I want to say, which is completely orthogonal to this, is that even you kept talking about the optimistic hypothesis and the pessimistic hypothesis, and I actually think it's the other way around. I think that the pessimistic hypothesis is that there's life everywhere, because even leaving aside doomsday arguments about intelligence being commonplace, and an empty sky meaning a great filter, even if there's a zoo thing going on, or a hard distance constraint, which could be overcome with Tipler probes, if intelligence is ubiquitous, then we are, at best, some kind of third world country or living on a nature preserve at the whim of the overlords. And at worst, they just haven't gotten around to making the intergalactic superhighway through our solar system yet, right? So I actually would like to point out that there's a way of looking at it that we are alone is the most optimistic hypothesis. It means A, no doomsday filter, and B, that the universe is ours. As opposed to just, we're Johnny-come-latelys and we have to submit to whoever was here first and their regulations and their eating habits and whatever it might be. So I just want to say that again, that I believe the optimistic hypothesis is that we're alone.
Oh yeah. Yeah, I think it's an interesting issue what to describe as optimistic here. In general, I think this framing, of course, is that we are social creatures, so we think being alone is always very bad. But on the other hand, there are different forms of competition too. So if you say, well, maybe the other civilizations are way better than us at creating value because they're old, they have solved philosophy, so now they actually know the meaning of life and they're really implementing it. In that case, we should be kind of happy because they're already doing it and we're getting much more meaning of life, whatever it is, done than we would.
We meaning the universe.
Yeah, the universe. So one can kind of take the perspective of the universe.
You have to expand your circle of compassion quite widely to say it's okay if the Earth gets wiped out or there's a great filter because intelligence elsewhere that we never know about perseveres.
Yep. You need to expand the circle of compassion at least 4.9 gigaparsec. So.
But I think that's a very rational thing to do. I mean, from the perspective of the universe at large, the idea of there being life everywhere is just a beautiful, beautiful thing. And there's the AI debate, and there's this whole idea of us giving birth to our progeny, and that's actually an incredibly beautiful time, even if it led to
But we can't get it wrong. We can't get it wrong, Will. And what I mean by that is, you may think it's a beautiful thing, but it's a very slippery slope to. Therefore, it doesn't matter what we do to ourselves, and until we have proof that they are out there. The conservative and sensible hypothesis, I argue, is that they are not.
But it's worse than that, isn't it? I mean, in a way, the kind of question you're raising is the question of veganism writ large. How much should we care about and indeed, compare our self-image, our self-worth, to the worth of, progressively more distantly related species through civilization.
Hypothetical species.
Yes, exactly. First of all, bearing in mind that in some cases they're hypothetical, and secondly, bearing in mind that we don't have any idea how much more intelligent or less intelligent than us they may be, or indeed how much they may vary from us on other spectra other than intelligence. Right? These are things that reasonable people can agree to disagree about. Therefore, I think what we need is a position that acknowledges the agreement to disagree. In other words, we probably just need to, figure out the most, all-embracing way of dealing with this uncertainty. And I think that what Anders and Toby and Eric did here is a first step towards exactly that. Now, which of them is more optimistic or pessimistic, I think really revolves around the intersection of all of these questions. And so I kind of agree with or I don't disagree with all of you, really. In other words, I think one cannot come to a conclusion about which is the preferred situation, because it's so dependent on one's position on these rather arbitrary spectra.
Okay, but my point is merely that, and then I'll shut up. My point is that we may not agree what's the preferred situation, but I think we could all agree that the least preferred situation is to believe without evidence that the universe is teeming with intelligent, conscious, beautiful life, and hence use that as an excuse for accepting our own extinction.
So, assuming that we're the only ones is almost a strategy for de-pessimizing.
Yeah.
You mean we'll look after ourselves better if we think we might be more valuable in a universal
Yes, and
sense?
until we have evidence otherwise, it would be very stupid to say it doesn't matter what happens to us because ET is going to
Because
be
we're not
beautiful.
the precursor,
We're very special.
But there is something interesting here about that uncertainty too. So Peter Akers and me, we're tinkering with a paper where we call 3 long bets about the distant future, where we're trying to at least formulate some of these assumptions and trying to see can one actually make arguments for and against it. So this began when there was a conversation between Toby Ord and Peter about, I think this was about technology. Is there an upper limit to technology? And on one hand, you can draw a diagram like Eric Drexler likes to do, where he shows these boundaries set by the laws of nature, and the light speed, quantum mechanics, gravity, they put some limits on what you can do with the technology, but there's a lot of awesome stuff in between. But implicit there is this idea that we're hemmed in by some various limits. So you might expect that eventually technology levels off. On the other hand, there are people like David Deutsch who actually think, no, this can actually go on forever in a meaningful way. You can also quibble about, for example, software, mathematics, they're kind of open-ended in some sense. But so the first bet was, by the point when we meet aliens, we kind of both reach technological parity. Because if the aliens are far enough, well, in that case, we can do what we can, what's possible. And then the second bet is, well, what about science? When you expand over sufficiently large distances, maybe the universe starts looking roughly the same. You've done all the particle physics you can do, you studied all the galaxies and stars, and once you seen a few superclusters, they all look alike. So it might be that experimental science also has a limit. It might be that it's actually some aspects of physics are not accessible. This is not as preposterous as it sounds. There are some aspects of cosmology that will become impossible to observe in a mere scant few billion years. There are some aspects of the background radiation that is getting redshifted to a degree that you actually can't see it. And the third one, which is close to this early conversation, is what about convergence on ethics? So we have reformulated the bet a bit, so it's not so much that the aliens are also following whatever ethics we follow, but by the point humanity maybe has spread out so much that the different parts are no longer in causal contact, it has actually converged on one or a few ethical systems, versus the possibility that it's going a lot. These ones are very, very different statements. The first one is kind of a statement on practical stuff we can do given the laws of physics. The second one is about what can be figured out. And the third one is kind of a mixture of weird meta-ethics and also some form of weird game theory. And we're kind of trying to write a paper about these things. And no, we have no clue about it, but we're having some people taking position on that to make it more fun as a paper at the very least.
I think like the last point on ethics, I thought was an interesting one when we talked about it on Wednesday, because to me at least, like ethics is this kind of ongoing negotiation amongst which intuitions we want to call values and which we want to dismiss as biases as humans, and it's very dependent on our evolutionary primary conditions. And so I would expect that different mind architectures that arise out of different evolutionary contexts, for example, that don't procreate, would have very, very different ethics. So I'm really curious. I could perhaps even imagine that something like coherent extrapolated volition for humans is true, and like eventually maybe humans with the same evolutionary background converge on one coherent ethical theory, but then how would very different mind architectures from ours converge with us on some ethical principles?
But it's worth noting that Immanuel Kant he seriously argued that all sufficiently rational moral agents will converge on the right ethics, which happens to be my ethics. And he made this very strong argument for this. So, it's an interesting question. Maybe that is just true for human-like minds. So maybe all sufficiently smart humans become Kantians, heaven forbid, but it might be something like that. But it might be that the Zorgons, who are totally different, they converge on something completely different. So it's a very fun way of trying to deal with ethics. And one of the nice things about the debate about AI safety is that it actually also has created a mirror to look at ethics in a very new way. Because traditional ethics was always done by humans thinking that, well, all minds involved are human-like. Maybe we can think a little bit about the poor animals, but that's about it. If you're religious, maybe you involve the angels, but they never do anything wrong, so ethics doesn't really matter much for them. Now, when you introduce AI, you suddenly realize, oh, we need to program something ethics-like. It might not even be an ethics. And that it gets into trouble because you can construct really weird pieces of software, really weird motivation systems, and suddenly it becomes actually a real thing you can discuss.
Yeah, Nick Bostrom called it AI ethics is philosophy with a deadline.
Yeah, so you need to finish by the deadline, and you also get the problem that, you can construct really odd things. So one of the fun things I discovered over the past 2 weeks, I'm writing a paper about the space of possible minds with Peter Eckersley. Most of what we're interested in is the kind of categories of minds we might construct or might run into. But out in that space, there are a lot of really weird ones. They're probably sporadic minds. They're basically individual pieces of code that change one bit and you don't get a mind, you get nothing like it. It all depends on totally bizarre mathematical coincidences, but they form these little fractal clusters out there of minds that we probably can't even find because it's kind of undecidable even without running them to find them. That's really cool from a mathematical and philosophical standpoint. It's also kind of totally pointless from a practical standpoint because we can't really build them. Yeah.
Has anyone considered, and I might be talking from a point of naivety here, that the most optimal mind and competitive ethics that lead to you being the dominant species on the planet and capturing all the resources, because it involves competition naturally as a function of it, and because there's no local competition in the solar system or the Milky Way or whatever, leads you to your own destruction because competition is a part of how you spiral up. So to acquire all the resources on the planet, you have to have an initial set of conditions in the competitive set that ultimately cap you. One, you have no competition, but not at that level.
Yeah, I can't name an author who proposed that one straight away because I drank too much wine, but it's kind of a familiar idea. So you find Carl Sagan, for example, saying that, well, maybe there is a lot of civilizations that don't survive. Actually, his paper from the 60s is one of the first papers really dealing with existential risk in a proper manner. And he's talking about this bottleneck and things, but maybe 1% may manage it. But they are, of course, the enlightened ones, sensible ones. Others have done versions saying, like, well, maybe carnivorous species are too violent, so they never really survive it. All the successful alien civilizations are herbivores, or some other trait. Now, it's very tricky. One can play around with these kind of arguments, but we don't understand dynamics of civilizations very well. And I think it's early days. We might be able to figure out a few things. I'm really fond of macro history, but I also think that Karl Popper is kind of hovering around the room as I goes, whoa, can we test this? Is this hypothesis falsifiable? I would, of course, immediately say, yeah, I want to run a computer simulation at least to try to demonstrate in models what would tend to happen. But it's tricky with civilizations because they are composed of individuals that might think different from each other. And some of them come up with their own weird ideas. And you can create institutions embodying weird ideas that actually contain and constrain behavior. So if there is one useful thing about civilization, it's that we can actually create these contrived things, sometimes just because of individual genius, that then actually allow us to survive. So I wouldn't exactly bet on this to be a generic thing. Similarly, there is the hypothesis that, well, maybe advanced societies transcend. They become better and better computation. They spend more and more time in virtual reality. Eventually, they turn into some little solid state civilization playing World of Warcraft or something like that forever. And we don't notice them because it's just a little silicon sphere hovering around its Dyson shell. That's a nice story, except that it doesn't account for Amish aliens. What about the people saying, oh, we should colonize the asteroids with using nanotechnology like our ancestors did? That's the one true way. So those guys would, of course, go off and do it. And maybe most of the offspring would say, no, World of Warcraft is way better. So, but there are going to be some of their offspring say, yes, being space Amish is really good. We should really colonize more asteroid belts. And then the Fermi Paradox breaks. You need to have a very, very strong convergence to get this work. John Smart is arguing for this. I disagree with him, but I think it is an interesting thing. Can one actually develop better theories about this dynamic? So,
the thing that always seems to explode the Fermi paradox for me is like the possibility that intelligent life, that our conception of intelligent life is extremely limited, that we wouldn't recognize it if we saw it, that the possible space for intelligent life is so much broader than we define it, and that it's, you know, it exists in different states that we're not even aware of, in different dimensions we're not even aware of.
Yeah, so that might bring up my big project, my book on grand futures. So Basically, a grand future is, suppose we survive and get our act together and become a mature species, whatever that is, and then we go off and do awesome things. Then the question is, how much awesome can we get? And the book is trying to quantify this, both by looking at what the laws of physics and some exploratory engineers tell us about the limits of that, but also doing a bit of value theory about the kinds of awesomeness. Well, going far, getting a lot of stuff, having a large population, having a lot of happy experience, doing a lot of computation. I look at a lot of the perspectives of this. But of course, whenever I bring this up, people will say, yeah, but what about if we're totally wrong about physics? And we can't rule that out. In fact, it's pretty likely that we're seriously wrong about important parts of physics.
It would be shocking if we're wrong about classical mechanics.
We kind of have that one nailed down, and it haven't changed very much over many years, although there are some interesting new insights. But on the other hand, dark matter and dark energy, we have had them around in their modern form for maybe 20 to 30 years. It's pretty likely that in 20 to 30 years we're going to understand them way better. So that is tricky. And there might indeed be entire new sectors that really, really matters. After all, we didn't know about electricity until a few centuries ago, and we didn't know about nuclear physics until relatively recent, although nuclear physics is kind of super important for how the entire world works. So it could be indeed that there is a big sector that we're totally missing. Maybe all the aliens are hanging out in the dark matter space because that's where the action is. But even more interesting, it might be that there is some sector that we're totally missing. So, for example, one area we don't understand at all right now is minds and consciousness. We don't have a good theory for that. And I don't want to kind of go and hand wave and maybe ascend to a higher level of consciousness. Although we are in Haight-Ashbury, right? So it might be appropriate to say. But that's at least one of the kind of obvious things we really know we don't know. So there are few things we should expect that we might be missing. However, I think even if you're kind of ascending to a higher level of consciousness, you might actually still be subject to the laws of thermodynamics. It wouldn't surprise me at all that you're going to see a lot of traces of that, because, for example, falling in love, it might fundamentally not be about information processing, but there is certain information processing that has to happen for that to function. Because even if it's qualia and consciousness and other non-computational stuff, there is also a certain amount of cognition and memory, and you know who you're in love with, that at least a few bits of information. Which means that now you need to do information processing, and Landauer's limit creeps up on you, and Maxwell's demon says, oh, you need to pay a few joules of energy in order to erase and modify bits here. And now that super civilization is going to be messing with entropy and thermodynamics, and that might be detectable. So I would be really surprised if you have these totally invisible civilizations, unless, of course, we're just cheating and simulating us.
Great.
I was just curious, because you mentioned not having complete laws of physics. Wouldn't basically admitting that throw away like all other uncertainties?
Not really. So think about what happened when Einstein overthrew Newton. Did the clocks in Switzerland stop working? No. Cogwheels work really well, even if you approximate them with Newtonian mechanics. In fact, we had cogwheels before Newton was born. We have a lot of the stuff we know works simply because we actually have observation of it. It's not like we could get any new law of physics that tells wheels don't work. We already have that. There might be really important sectors, might be even sectors where most of the value are located. Maybe it turns out that actually there's some kind of consciousness physics, and this is where moral value and all the important stuff actually happen. So if we discover that, we totally skip all this boring stuff about space because we found something way, way better. But that uncertainty still doesn't mean that we can't say anything about the actual world. It's just that, yeah, we are going to have to deal with this nagging doubt. But that's the best we can do. Saying, oh, we could be wrong and hence we can't say anything. Yeah, at that point you maybe win in the philosophy seminar, but you're not actually going to practically function in the world.
So you mentioned the books about how awesome the future can be. So how awesome can it be?
Whoa.
Especially in regard to entropy.
Yeah. So,
What are we gonna do?
so on one hand, I have a very, very bad news. I actually believe we have a finite future. It doesn't look like I can squeeze out an infinite amount of computation. This is very sad, of course. I grew up reading Barrow and Tipler's Ventropic Cosmological Principle, and those final pages in the final chapter when Tipler outlines his omega point theory, where advanced civilizations in a collapsing universe control matter and energy to do an infinite amount of computation. Oh, I got religion from that. That was awesome.
Asimov's last question.
Yeah, and well, I'm really hoping I'm totally wrong about it. But as far as we can tell from the physics we understand right now, so we can go out into space, and I have this paper about spamming the universe, where we essentially outline how using a little Dyson shell, you don't even need a complete one, and just an afternoon of sunlight, you could send seed probes to all reachable galaxies. It turns out that you can't reach all the galaxies we can see because the universe is expanding, so there are some galaxies that are too far away. You will never reach them because they will accelerate away from you. That acceleration is really pesky, and that's why we can only reach about 4.9 gigaparsec away. That's just a few billion galaxies. This is an enormous scale. It's much bigger than, you might have seen these big pictures of the galactic voids and the branching superclusters. Those pictures are smaller than this scale. We actually don't have a map on this scale because the galaxies are so far away that we're rather hazy on the distance. Now, that is, there might of course be faster than light travel, but I doubt it because that also implies time travel, and we would not just have to deal with aliens from very far away, but also time traveling in future, humans and aliens. And they haven't shown up yet, as far as I know. Nobody came to Hawking's funeral, which suggests that they're not around. So we have a finite amount of stuff, and this is interesting because we can maybe go out and grab that. We can become that stuff and use it for whatever we think is useful. But it means that in the long run, if we have to pay a certain amount of entropy in order to do computation, eventually we will run out of stuff. Now, there is an awful lot of potential computation you can do with billions of galaxies. And when it comes to time, many people talking about the far future say, yeah, in trillions of years the stars will go out, and then we kind of hint that that's the end. I think that's just the beginning. I think the cool stuff really starts once the last stars really go out. I'm very much in favor of red dwarf stars. They're amazing little Volkswagen Beetles of stars that keep on going and going and going for trillions of years. But they heat things up. I think actually the real future is going to be that you use these condensed objects in the degenerate era. That's where you can do a lot of computation. But probably proton decay, if it happens, will get us in kind of 10 to the 36 years. But that's an awful lot of time to do an awful lot of interesting stuff. Now, summing up, it seems like you get something on the order of 10 to the 120 irreversible operations. That is how much computation we could do with the stuff in the universe. It also turns out that between these irreversible operations, you need to pay this in order to do error correction. There could be reversible operations that don't have to pay an entropy cost. Now, so what we came up with this Wednesday, Adam Brown pointed out that is there a polynomial amount between here? Then you get something on the order of 10 to 120 operation. That's a vigintillion.
So say, what did we call it in the end?
Well, I call it, so this, if you have a polynomial, we get 1 vigintillion operations, give or take a lot of orders of magnitude. But it might also be that you can get an exponential number of operations in between. In that case, you get 10 to the power of 10 to the power of 120. That's a vigintillion plex operations, which is really, really awesome. This is an absurdly large number. It actually changes a lot of strategy. In fact, it turns out that you get into trouble because of time limits. If you have a time limit like 10 to the 555 years or so, you still don't have the time to get through all of these operations. So it's still finite, but it looks like the potential for it to be ridiculously big. And then, of course, just to conclude, we might want to use this to produce happiness, pleasure, insight, love, or good philosophy, or whatever it is that gives life value. And that's, of course, where we get over to a lot of very fun value theories that have very different prescription of what we ought to use this for.
Anders, there's a term that's not in the Drake equation, which maybe should go on the end. You alluded to it, and that is sort of the difference between intelligence and consciousness. So
Yeah.
that seems like what we have some of the greatest uncertainty about. Is and do you think that's even important? Like,
I don't know. So on one hand, a lot of people tend to assume that if intelligence is not conscious, it doesn't count morally and it's not a good thing. We generally tend to have this idea that if we get a super civilization but there is kind of nobody at home, that's a bad thing. Nick Bostrom's paper on the future of human evolution is actually quite scary on that.
Disneyland without children.
Yeah, which I think is a beautiful description of it. Charles Stross in his Accelerando has this end state of economy that turns into this consciousness-free, very efficient, expanding thing. And that's not very fun if you're a conscious being actually think value comes from being aware of your existence. Now, I'm not entirely certain that non-conscious systems are value lacking. In fact, I've been listening to some ethicists thinking about animal rights, and some of their arguments seem to make sense without invoking consciousness, because it's about goal-directed systems, etc.
well,
And
they've
it might
never lived with animals if they think animals aren't conscious.
Now the point is, they think the animals are totally conscious. It's just that I realized that argument would be true for a robot too. A robot that's not conscious. If you have, and that is the intriguing part. You might imagine that there could be systems that actually matter morally but we're not conscious. I
So
think
the paperclip maximizer a good scenario?
probably not. It might be. Imagine that it's a reinforcement learning agent, and actually a reinforcement learning agent succeeding very well. That actually does provide moral value. In that case, if it takes over the universe and turns into paperclip, maybe that's the best outcome. I think most of us are rather skeptical about that. I don't think it's just that something maximizes something gives it value, because we can very easily make maximize of any arbitrary stupid thing. The very interesting part is what does give value, and this is a super deep question. Axiology, the branch of ethics that deals with the nature of value, it gives me tremendous headaches because there's so many different options here. It's just that it's not clear to me that consciousness has to be in there. It's probably likely. It might be the one thing that bridges it, but it might be that there are other things. It might be that when we meet aliens, if we do, they have, consciousness. No, we never heard of such a thing. Now, we happen to have this consciousness, which is super important to give value. But you humans clearly don't have that. You definitely need to have these particular quantum crystals, and you don't, so you can't have any more of that. That's a possibility.
So how can you think that those different entities can converge on one ethics?
I don't know. One of the loveliest things for me about being not trained as a philosopher, but working at a philosophy department is I don't necessarily have to take side. I just say, just work here. I'm curious about the different theories and see which ones make sense, and some of them probably don't make sense. So you really want to get in on this.
Yeah.
Well, I want to get into on the ethics of conversion, and I'm really glad we got back to that. And then I want to throw in a curveball right at the end, because I think that this conversation is on a bit of a stage that is a curious one that needs at least scrutiny. But the ethics of conversion seems like a pretty likely thing in my mind for two reasons. One is, as intelligence evolves, it tends to expand, from itself to its tribe in terms of its sphere of caring or whatever you call it. And so naturally, you get to a point where you go and care for all life, and you get pretty abstract and let's say accommodating on your definition of life. And so in that scenario, it is almost always going to be that most of life cares for most of life, and therefore you are going to end up converging in the most part.
Well, that's some humans. Like, in modern
I would actually say this is a very mammalian sentiment. I think a mammal would totally agree with you. But I'm not certain insects would.
Yeah.
Okay, but let me try a different tack then. And the second point was that if you get to a point of intelligence where you invent AI that's not linked to any reptilian brain of any kind of bias towards those sort of fundamental things, because if we give birth to our progeny as AI, then it hasn't got that reptilian stem, if you like, to be connected to, and therefore it isn't got the same bias, and then maybe it all plays on that abstract.
Well, it might if the human race is the one birthing the progeny, and the only training data we give it is based on our own experiences.
Fair enough. There's a link there, but it gets more tangential as you go. No?
And it could be unsupervised. And
But-
need any training yet.
But can I just throw in one slightly more of a curveball thing, which is that the whole stage of this discussion seems to be about space-time. And I just gotta wonder, I mean, my old boss at NASA, he used to say, well, you know, to the Fermi paradox, is like, well, maybe they just go into a different dimension and they become nano, different timescales, different, they just go off into some sort of different place. I'm glad you brought up crystals or, you know, other drugs or whatever. You can imagine that maybe that takes you into different places. The whole thing about it being limited to the space-time concept that we get so focused on because we train to throw spears and shit, it's not clear that that's the right framework to be thinking like this. Now, I don't know how to bring that into the debate in a sort of even useful way because it's so vague. But do you see what I'm saying? Like everything is about.
I think the fundamental problem is, yes, of course, there could be stuff we can never detect. But in that case, it probably actually there is no point in doing much about it. It always remains a possibility.
Well, also just in a few years, it might be that we don't care about it either, because you get to some certain level
Yeah,
of intelligence
but-
and off you go.
But when
into
we're
somewhere
having
else.
this argument, and especially when we try to make a decision about the here and now and where do we want to go, we need to act on what we know and what we suspect.
Well, right, but I mean, can't we use the same kind of logic that I was putting forward in challenging your paper? In other words, looking at the trajectory of rate of discovery of things that seem to be in that kind of space.
Yeah.
You know, if that seems to be slowing down, then we can say one thing. If it's not slowing down, we can say a different thing.
And this also goes for a lot of other domains. So one of the best ideas, I think, to ever come out of our institute is the crucial considerations. So these are considerations that make you change the direction you're going in. If you realize that, my compass is broken, I've been walking in the wrong direction, you should turn around immediately. That's an important, crucial consideration. Now, in some domains, you constantly get crucial considerations, and that means that you're really confused where you should go. And typically that means you need to do way more research before things get clear. In other domains, it's very rare that you get these big updates that totally challenge things. Now, the cool thing is we can actually estimate roughly in a domain how many crucial considerations we should expect. There is something called the Turing Good estimator. It's actually I.J. Good, the guy who came up with the intelligence explosion, who was working together with Alan Turing, who did some work on cryptography that he might be mildly famous for. Might have been some computer stuff too, but he's mostly known for his biology work, of course. But anyway, they have this way. It's about estimating if you see items showing up. And sometimes there are new categories. You can make an estimate based on the past number of categories you've seen and the number of items, a probability that you will see an entire new category.
So I have a question about that. I haven't precisely heard of this. So, I mean, to what extent is it the same thing that I was saying? To what extent is it a different thing? I mean, for example, the kind of thing I'm talking about, the canonical, identification of a missing link that we hadn't thought of before was Darwinism. Right, the very first step in providing a missing link, if you like. Does this fit into that kind of thing, or is it qualitatively different?
I think you can use it in a lot of different domains. So one fun approach is to say, how often do we discover kind of new sciences or new paradigms in science? And I haven't done a proper survey of that literature. I tried to do it in some domains. So in the book right now, I actually have a list of various physical things that are kind of important for my model of the future and how long we have known about them, because that gives us a rough guesstimate of how stable they are. So the real problem here is, of course, this is not always applicable. People try to use stuff like this to estimate how many undiscovered species are there of a particular kind. And this is very, very uncertain, but you can do guesstimates that are not terribly bad in some domains. However, when you apply it to some domains, it also turns out to be not quite as easy. So I tried it, for example, on elements, and it turns out that first the rate of discovery of elements was kind of very low, and then we invented alchemy, and it went up, and we started finding new elements. And then it speeded up when alchemy became chemistry. And then at that point we also figure out finally what the periodic table was in quantum mechanics. So now we actually knew the answer. But when we started making new elements, so that curve kind of broke because we changed the rules of the game. So that's what to look out for. That's what would undermine looking at the past. But looking at rates of discovery leveling off, that is a hint that we might have covered most crucial considerations in a domain.
What's one field with a lot of crucial considerations potentially left?
The most obvious one is kind of quantum gravity. It's kind of mega obvious. We actually haven't got a proper theory, and people are coming up with arguments that are totally wrecking all the other arguments back and forth. It's very chaotic. When it comes to dark energy, well, there we have so little data that you can't even say that we have gotten many items. We don't really know what's going on. I think our understanding of neuroscience is also, there is a lot of, it's pretty important for many things here, just like artificial intelligence. And again, we're discovering a lot of really interesting things. To me, it was really mind-blowing to see the revolution of kind of the 2010s in neural networks, because I used to work in neural networks before it was cool, before it worked, before you could get a six-figure salary from it. I remember asking my professor, those deep neural networks that Schmidt-Huber guy was going on about in the 80s, they look cool, should we do something about it? And Professor Lansner very sanely told me, no, Anders, it didn't pan out very much. They didn't do much more cool stuff. And he was right in 1997, because they didn't do anything cool in 1997. We didn't have enough computers and data. They did cool stuff in 2012. And the fun thing is experts and people who know their stuff in neural network, even the people who've been around there for a long time, were surprised by that. So I think we should expect loads more surprises in machine learning, which is mildly frightening.
Yeah, I think that if, one thing that the paper that you wrote on Dissolving the Fermi Paradox, afterwards I went around just thinking, oh my god, if this is the way that if this turns out to be true, then a lot of papers have been published on the assumption that the drag equation and so as it is correct, and that kind of gave me a lot of epistemic humility for going forward in other domains as well. And I think Aubrey, you mentioned that one thing about the paper was that in hindsight it was obvious, and so many. I just wonder how many things there are out there where we just assume something and then base a whole house of cards on it.
Well, sure. I mean, I think this is definitely humbling for all of us. Whenever this happens, whenever these breakthroughs are made that are in hindsight fairly obvious to a lot of people who are in even peripherally related spaces, and of course, thinking from a personal perspective, it reinforces the historical success that has happened when people switch fields. As many of you know, I was originally in artificial intelligence. I switched to biology. I was doing pretty well in my first field, but I did a lot better in my second field. And the whole molecular biology was invented by a bunch of physicists. This is something that happens. And I think it's the same kind of thing. Kuhn tried to say it. A lot of people have tried to say it in different ways, but we have no idea what really makes obvious things so hard to see. And if we could figure that out, science would move quite a lot faster, and so would technology.
All right, if we perhaps speak.
There's a number that I think would be fascinating to know, and it's like of all the things that are knowable, what fraction of them do we know?
Yeah.
And I think I would argue that that's an unknowable number. But if the answer was 1% or 0.1%, that would be really exciting. And then if the answer is like 0.0000001%, I would be like, well, what the fuck are we doing this?
Yeah. Well, I think you're right that it is unknowable, maybe in some very strict form. It's a bit like Chaitin's omega constant, which is the probability of a random program halting. That is an uncomputable constant, but it's a number between 0 and 1. It's well defined. There are even a few papers calculating a few digits of it, which is pretty hilarious because it's uncomputable. But you can get away with it when you do the right kind of trickery. Now, I think we can't know how much is knowable. That's almost by definition true. We can kind of look at how much of how much can we search? And we could make an argument on the order of that. Okay, we got 10 to the 120 calculations we can do. So so in some sense we might say, yeah, we've done a small fraction of those, so we know we've done more than that fraction. So I did some calculation actually on how much evolution you could do in the future universe, and I felt that it looks like so far we've done probably on the order of 10 to the minus 77 of all possible evolution if you wanted to have biology and...
are you a bit worried about the number of significant figures there?
Yeah, exactly.
10 to the 10 to 120 in the first place.
Yeah, so one should probably not take those numbers too seriously. Again, one should recognize very like the Drake equation numbers when you don't use your uncertainties in a particular good way. They're very sloppy. It's just, yeah, some super humbling number is pretty likely. On the other hand, we should not miss that we actually know stuff. I'm constantly annoyed when people say, oh, the brain is so complex, we don't know anything about it. Wait a minute, we know an awful lot about ion channels and synapses and how certain drugs affect it. That's kind of okay. It's just, or is there likely to be something totally different about the brain that we totally miss? Well, we're not good at consciousness, but some parts we actually have nailed down fairly well. There is a lot of stuff to discuss. So people quite often play this game of trying to be mega humble and say, we don't know anything, which is kind of cheating.
Yeah, I would like to say something about that because it's one of my major complaints about scientists. And I feel that it's something that everybody needs to be not only aware of, but aware that it's a huge problem. This celebration of ignorance, which you described, is something that I believe is completely fundamental to the mindset and the way of thinking of the overwhelming majority of basic scientists. Basic scientists are trained and motivated and, focused on finding things out for the sake of finding things out. The only good questions are the ones whose answers would create more questions, right? And this is a massive problem because there are many areas, including of course the area of the biology of aging, in which until fairly recently we have been unable to make a good case that the knowledge we already have can be translated into a strategy for doing something about the problem that we're studying. But we suddenly can, and therefore we've done well better start realizing it.
Yeah, I think one thing that we discussed was at least the thing that we would really like to know is generally when the universe favors offense over defense over the really, really long time.
So just to finish my point, I mean, I often use the immune system as an example of this. The immune system is a hugely complex system that nobody in immunology would say we are anywhere close to understanding completely. But 200 fucking years ago, we started understanding it well enough to start saving ridiculous numbers of lives.
Yeah.
And, when we understood a tiny fraction of what we understand today, let alone what we will understand 100 years from now.
And I think this is an important point you're making, that quite often in basic science and philosophy you often get rewarded for saying humble things about ignorance. And I think we should recognize that epistemic humility is super important, but that's about uncertainty. That's not celebrating ignorance. This is where I really started to appreciate engineers, because engineers try to build stuff that actually works. And sometimes they don't even have a good theory about why it works. But if you demonstrate that this works, and you add a lot of safety margins to handle the uncertainty, that's really, really fine. Yeah, and I think we should recognize that the engineering mindset complements the scientific mindsets in a beautiful way to actually solve real problems.
Anyone from Calico here to transmit that?
Eliezer Yudkowsky wrote a couple of things about wrong or harmful epistemic humility, which is quite nice to check out, I think. But I think one of the questions that really struck me as a question that could even be asked was the one on offense over defense over the really long run, and I'd be really curious.
That is a super important and really interesting question. Generally, in the long run, if you have access to the ultimate technologies, will the attacker win over the defender? That would set the character of the universe, I think. So we know in some domains right now, for example, there's a kind of truism that in computer security, generally the attacker wins, mostly because the defender has a crappy system that is not built to be very secure. We could try to build secure stuff, but so far, because of various economic, political, and other reasons, we haven't done that. But in principle, it might be different, but many people are skeptical even of that. So there is this question, if the universe in the long run is that, anybody can kind of blow up anybody else, that's going to be a rather scary universe and you better hide in a lot of dark corners. On the other hand, if it turns out Defender wins, now you can, for example, take your galaxy and keep it and say, okay, I'm going to sleep now for a few trillion years until it's nice and cool, and nobody's going to take it from me. So you get very different strategies. And the cool thing here is offense and defense is basically physics. There is, of course, a lot of strategy going on, but deep down it has to do with the nature of a physical law. So I'm working on an appendix which is kind of really weird about, can we actually say something about what the laws of physics indicate? I don't know the answer to this. I'm hoping to figure out more of it. There is a recent paper coming out of FHI by Alan Dafoe and Ben Garfinkel about what they call offense-defense scaling that argues under certain circumstances, as you get more resources. At first, offense gets more powerful, but then defense scales better. So actually on the larger scales, the universe gets peaceful. If that's true, that's kind of almost the best news ever. We need to read that paper, scrutinize, and figure out how to build on it.
Yeah, then we
Jim had a
just
question.
cross the risk time horizon, and then we're basically there. And I was wondering how that relates to the other paper that you were writing on the kind of on outrunning the law. Because you mentioned in that paper, I don't know if anyone's looked at it, but that there's kind of like two ways that it might go. So either you might be able to do like a really quick exodus, in which case you try to outrun the law, or in the other case, you might want to do a very quick expansion.
So this has to do with the expansion of the universe. So basically, if I get into a sufficiently fast spacecraft and leave now, and you realize tomorrow, Anders snuck away, we need to stop that bastard. You need some faster spacecraft because I'm going over the cosmological horizon and I get my own galaxy somewhere far away where you can never reach me. That might be good news or bad news depending on who it is doing this. You might say this is the ultimate libertarian dream, kind of homesteading on the ultimate frontier. Or, oh no, a lot of people with really creepy ideas get off and we can't stop them from doing creepy stuff. We'll never know about the creepy stuff, but we know they exist out there. So there is an interesting problem here about the expansion. And this has to do with accelerated expansion. Generally, it turns out that in the universe, waiting for a while but then going much faster tends to win unless you wait for a very long time. So actually, if a space police spends 1 million years of building a faster spacecraft, they can typically catch up with you. There's some interesting physical limits here on how fast you can go. Inside the galaxy, if you're moving very fast, you run into dust. We don't really know how much interstellar dust is kind of gravel size that tend to blow up spacecraft. But it might exist. I think it's looking pretty good unless you go along the galactic plane where we can see kind of obvious that there is a lot of it. If you look towards the galactic center, you see a dust lane. That means that all the photons between you and galactic center hits something. Much of that is small, but a lot of it is dense. And even if it's not a dust grain that hits you, even hydrogen gas, when you move at relativistic speed, is a proton beam. So you better have good self-repair and radiation tolerance for your ship. Meanwhile, intergalactic space looks very clean and pristine. It might not be perfectly clean. There is a bit of gas bubbling off from galaxies. There is something called galactic fountains where hot blue-white stars create these fountains of gas leaving galaxies, and they might even be circulating and raining in. But generally, intergalactic space seems to be much more long range. So you might want to maneuver gingerly around galaxies, or use the gravity field to do a kind of ultimate gravity assist. You can essentially use gravity lensing to think about how to actually steer your relativistic spacecraft. But the cool part here is, of course, how fast you can go. And there is probably an upper limit that's practical. And trying to go a bit faster means that you probably need more backup copies, and they go up exponentially. So eventually you are going to run out of those resources. But how much you can control in space is probably more based on causal connectedness than speed of the space police spacecraft. It's more like where can you actually observe that something is going on and send somebody over. Old empires had a size that was kind of set by the time it took to tell the emperor that, oh, the provinces are rebelling, and then he's showing up with his army. But if the province had enough time to raise their own good army, well, no, we can't keep it together. This is, of course, why you want to have governors, and you want the governors to also have incentives so they stay in. But if you have a big enough space empire, this might be tricky because of expansion of the universe. And in a few 100 billion years, all the gravitational bounds in the galaxy cluster are going to get separated from each other. So we're right now in the era of connection. Right now, you can go almost anywhere. But in a few 100 billion years, you get the era of isolation. So if you are in a galactic cluster, you won't be able to get to any other. Again, you might have this libertarian solution. I get my own galaxy cluster and I make my own rules here. Me and all my copies and descendants and whatever. The problem might be, of course, that we want to coordinate before we get to that. For example, maybe it's possible to trigger a vacuum collapse. That might be a very stupid idea to do before the era of isolation. Then we might say, yes, up to everybody to mess with the vacuum if they want to, because it's going to be a local problem. It's not going to affect everybody else. But then we need to coordinate so nobody actually tests vacuum collapse too early.
Yeah, it also reminds me tangentially on the paper on astronomical waste by Bostrom. And well, I was wondering, given that those are the options on the table, so what initial conditions could we set in place right now actually to make positive futures more likely in that regard?
So one wonderful idea Will MacAskill has is the long reflection. Before we set out and become causally disconnected, we might actually want to think through the stuff we need to coordinate. So I have a list of ideas. This is kind of one brain reading a few papers and thinking a little bit about it, but probably more brains would be able to come up with way better ideas, especially if you're wiser people and who read more philosophy, etc. There's probably quite a lot of important coordination things we ought to do relatively early.
What's on your short list?
So on my short list, most obviously you don't want to have too much conflicts. So you probably want to set up things so you don't have space wars. So there are, Phil Torres, for example, he's been arguing in a few papers that maybe colonizing space is a really bad idea because you might actually get a lot of conflicts because you have different societies that have very little in common and they might actually have reasons to attack each other. I think that's somewhat unlikely because of the trickiness of space war, but there is an important issue here. You might be doing battles in other ways by diplomacy or other things. Certainly self-replicating machines, yeah, they might really mess up things. They might be vermin. You might want to at least have some rules on how your von Neumann probes get to behave and so on. Vacuum collapse is another obvious one. We might also just want to have a very big crypto party and sign a lot of public keys and have a quantum bit pairs. So when we spread out, we can communicate in a safe and reliable manner. There might be that we want to do galactic engineering.
Is there ICO on the horizon?
Actually, I was kind of hoping I could avoid it, but there is going to be a mention of blockchains in my book. Because there might be a problem of making deals that stick over very long distances in space and time. So you might want to set up these things before you set out. But this is just the stuff I come up with right now. There are probably more important things. And right now we're a third of a second away from each other. We're all really close, we're all on the same planet, and we're not very well coordinated. But we can work on becoming so coordinated that we actually get a stab at coordinating about what really matters and figuring out what really matters when we get to that coordination.
Like, I think two coordination things that we discussed was, one of them was, well, perhaps there's some, let's call them the Amish that want to stay on Earth, but others want to explore the rest of the universe, so there might be a coordination problem there. And then another was that, maybe, I want to hibernate for a little bit and then only get up later when it's really worth it for me. And I'm wondering, how can you even make sure that those coordination problems or that those agreements would be held over long time horizons or space horizons?
Yeah, so it's worth noticing when I talk about grand future, I tend to do this cosmic big thing. And a lot of people just recoil in horror from this whole stuff. They don't want to know how to move a galaxy. They don't want to see galaxies move around them. They want to have tea with the vicar in a nice little Cotswold village and watch the cricket on the green. And I think this is a very common human view. You want to have nice social relations and meaningful, none of that weird, strange stuff. And I think they might be totally right about their own values. I want to be kind of steering galaxies around. It's going to be pretty fun, I think. But we might want to make a deal. You get Earth, and we take the rest of the universe. I think that's a really fair deal.
So like in meditations on model, there's, you know, the end scenario of like where I think Scott Alexander disagrees with Nick Boston, where he says you can't even just have a garden. The walls that you'd have to set up in the garden are like too high, like, and eventually the competitive forces will just even like force Earth to be angry.
So Hans Moravec, for example, in his book Robot, he's suggesting that we leave Earth to the humans who are living this idyllic life thanks to AI, and then the people who want to go weird and post-human go to space. But he actually noted that sooner or later they're going to come back, they're probably hungry or really going to weird up the place. So you want something that can stick. And that requires some form of coordination. So it might be that you have a big blockchain, it might be that you have a singleton, it might be some very different form of coordination. And as you mentioned, you might also want this to work over time. We might want to coordinate so the estimators can kind of sleep and say, okay, kids, you play around with the physical universe, we just want to do our virtual stuff, but you leave enough stuff for us to do that in the degenerate era. So you need a firm coordination here. Yeah.
There's an intractable problem here if, let's assume everyone's of the same intelligence, has the same ideology of believing that, say, hibernation is the optimal thing.
No, that's the point. You want people with different views. You want to do a moral trade. So I might want to hibernate and you think that's a stupid idea. So you get to play around with the universe now, but then you leave mass energy for me in 1 trillion years, and then I get to do it. The question is, can you set up a trade that works like that? So in normal society, we have various institutions that actually allow us to have very, very different views, and that works well. Here you have a challenge of doing this over very big space-time distances, and probably between entities that are really different from each other. You also, I'm not going to have time to get into it, but the really cool game theory that happens when you start thinking about these enormous distances. If you also have that, we humans meet the Zorgons and we make a deal at the border, but if the time it takes to the news of a deal getting into the human and Zorgon space is going to be so long that parts of them expand away. There are some systems that would be totally fine. It might turn out that we humans converge on maximizing happiness. We have computers full of very happy mindset, and the Zorgons would calculate digits of pi.
I'm going to ask a really stupid question. Yeah. Okay, because my physics is so old. How does entanglement complicate all of this?
A bit. You can't communicate using entanglement in the sense that you get faster than light transmission. You can send extra information using quantum entangled particles. There is something called the Holevo bound, which I'm not super good at. I'm going to totally have to reread quantum mechanics and quantum computation to write those parts. But basically, if we have exchanged a pair of entangled particles, then we can squeeze a bit of extra information between us. We can also correlate our actions in very clever ways. So, for example, we might, if we are expanding at different parts of human space, and I meet the Zorgons, so you might meet other aliens, we want the deals to be correlated in some sense. And this is again something we want to make up before we set out. Okay, if we meet aliens, what kind of bargaining strategy are we going to be running here? So you can use entanglement for some very, very clever things. Given that it's very early days for quantum computing, this is another area where it's bound to be loads of crucial considerations. We're just discovering now what kind of cool resources there are in quantum communication. So you have classical information, you have entanglement, but you also have a third one which I forgot right now. I'm blaming wine, which was very tasty, but there might be very well a 4th or 5th or 6th one there too.
All right. Well, I think one thing. I think there's many questions left, but I think one thing that was interesting to me is that writing a book on the far future kind of assumes that we'll make it there, and so how are you like relatively optimistic
Yeah.
about it, especially in the face of AI?
Yeah, so we used to have this graph on the whiteboard at the office where people were making marks for the probability of existential risk this century. And the median was about 12%. Now you can view that as a super pessimistic outlook, because that means that you're more likely to die of existential risk than a whole host of cancers that people are worried about. But you can also turn it around and say, well, it's 88% chance that we survive this century, and at the end of that we're going to be way more powerful and wise and so on. So I'm very much of a glass is half full view here. So I do think that, yeah, I think many of my colleagues are unduly pessimistic about AI. But I also think that, yeah, there are very good arguments why AI could be super dangerous. So even if I think there might be a few percent chance that AI is really dangerous, which by our standards is a very, very optimistic and maybe even naive view. But that still means that we need to do an awful lot of AI safety work, because a few percent risk, that's not okay. I'm going to get onto an airplane tomorrow, and if I was told, oh, there's maybe 5% chance that it's going to crash, I wouldn't set my foot on that plane. So we really have a good reason to fix AI, especially since it's such a useful component for getting to the grand future. Yeah. So in an early chapter in the book, I'm dealing with the mere post-scarcity societies, just how glorious could the material world become. And it's pretty clear that if we manage to get good atomically precise manufacturing, we can make a lot of solar power, and we can make relatively low energy machines. So now we can recycle and get all the material stuff we want. But that's just the old-fashioned view of a really good future, because being able to have a lot of stuff, that's not really what's going on in this city. This city doesn't manufacture that much stuff. However, it does services. There's a lot of important things that are happening here that require intelligence of some kind, or at least charisma and other things. And getting AI means that we could get a lot of that. We would be post-scarcity for services too. And of course, if we get super intelligence, now we're post-scarcity for good services. And we might even be getting some wisdom if it's really, really good. So I think AI is kind of a key for post-scarcity. Even if you have very modest AI, even if it's just animal level, that's going to be so useful for making self-replicating mining machinery. I mean, going to the moon and having astronauts dig with shovels, that would be rather sad. You want to have machines to do that. You want to automate this, and then you want to figure out how to automate the automation. And before you know it, you're happily on your way to your first Dyson sphere.
Yeah, we had a workshop recently on AI for atomic precision, and I think the effect of AI on other technologies is I think something that is often neglected just in the hype on AI. Do you think there's any risks that we're neglecting right now in the hype of AI? So I think Cristiano here last time mentioned biotech risk.
Yeah, biotech is kind of an obvious and scary one, because we're getting a lot of really impressive power. It's very dispersed. We don't really have a good idea how to control many of it. So we need to work on the biotech risk. I think those are the two big ones. We shouldn't forget about this kind of boring, old-fashioned nuclear war risk. It's kind of still hanging around. It's really an annoying thing that the interest in different risks has these fashions. But also, there are people who understand nuclear war risk and are working on diplomacy and making sensible control systems. So it's not exactly neglected. It would make do with more people. I think right now the really neglected risks are probably still AI, because there's a lot of work we need to do there, and there's a lot of interest in patching. Biotech is another obvious one. It wouldn't surprise me that there are some neurotechnological risks that are further afield, which would be way more weird and creepy. And it's one of those information hazard things. I don't know even whether we ought to be thinking about neurotech existential risk. On the other hand, not thinking about it might also be stupid. So there is a meta problem there. Generally, I'm rather optimistic about this, because sometimes it turns out that things that people believe are super dangerous turn out to be less dangerous. So for example, for a long while people were really concerned that nanotechnology or atomic and precise manufacturing was super dangerous, but typically because people got kind of obsessed about self-replication, which is not a problem. But it seems now that we have good reason to think, now that's mostly helpful. The real danger is, it's making it so much easier to do a lot of other stuff. Okay, that's kind of a little bit too much of a good thing, but that's probably something we can manage much better. So it wouldn't surprise me that maybe 20 years from now we're going to be kind of laughing, yep, we were so concerned about the AI problems and finally we found that theorem and now we're pretty well in a good position. But we better get to that point first.
Maybe, as a final question, so I think, we talked about the kind of like possibility of a Disneyland without children, right? And I think you are painting a Disneyland with children for us in the future. So what would we actually need to do? Like, I think you're signed up for cryonics, which is great. Who else here? Anyone else? Great. Okay. Yeah. I'm hoping I mentioned this every salon, so eventually your hands will go up.
Yep.
Anyway, so what do we need to do now? What are the next steps forward to get there?
So reducing existential risk is a kind of nice one, and there are various things one can do. I also think spreading the right kind of optimistic mindset. So one of the best concepts that has come up recently is Eric Drexler's idea about Paretotopia. If the pie becomes much bigger, even if we're all very competitive, we should all realize that we want to push in the direction of a bigger pie. Because we are very likely, each of us, to get way more. Even totally selfish competitive actors would not want that. There are some psychological issues about this, but basically, if you think the future is actually going to be very positive sum, or could become that, that changes your mindset. The zero-sum mindset is very pernicious, because that means that, oh, I need to make sure others don't get stuff. It means that, oh, I shouldn't be cooperating with other people, because then I'm going to be in a worse situation. And I think one of the biggest risks right now when it comes to AI safety is that you get an arms race where people think, oh, it's in our natural interest not to share safety information with other nations. That's kind of stupid. You should totally share information, at least about safety, even if you're competing. And if you can recognize that, oh, the cake would become way bigger, that's a good reason to cooperate. But getting people to understand this mindset, explaining it in different ways, that needs to be done in a lot of different ways. I like to draw diagrams and do game theory. That doesn't compel politicians very much. We need to other ways to express it, whether that is from song and dance, or in art, or in the white papers, or expressing it in particular political agendas. So as a final point, I think, we need to learn how to speak more languages. Not just in the sense of actual linguistic language, but also the language of different cultures and different political constituencies, and get them to understand it. Even the people we think are those guys, those people we don't really want to talk to, they're typically against existential risk. And we might actually get them to our side in many relevant factors. And that, I think, does help the probability of getting a really awesome grand future.
Yeah, I think that one thing that crucial consideration teaches you is to look at things that are uncontroversially good, perhaps that, and I think that's one thing. Paretotopia would be one of those things, right? It would be hard to argue for anyone really that would be a better future.
Well, you will find a philosopher arguing, of course. There is, for any question, there is a philosopher who is arguing for the opposite, just because. And you can make arguments saying, yeah, actually it's better that the world gets destroyed than that we all get rich, but it's a bit unequal. You can make that argument. But I think it's a stupid argument. And I think most of us think it's a stupid argument. And even if there is some merit to that we want to have more justice, well, we can find other ways of fixing the justice as long as we have a big and healthy world.
Yeah, I think, thank you so much. I think it was incredibly inspiring to have someone here who is so optimistic, and I think it ties in well with existential hope, which is a concept that originated at FHI. And if you want to follow up on any of the readings that we've been throwing around, I have the website existentialhope.com, on which I list all of his stuff and much more.
And thank you for all your questions and comments and interventions. This has been so much fun.
Yes, I think so too.
Thank you.
Things about how to just stay in touch with Foresight to close this off, but for my end, thanks a lot. It's been tremendous fun.
So we can stay here. Some of you, a lot of you actually, which is amazing, wrote us or asked us to rescue how you could help with Foresight mission to advance beneficial technology and help sentient life thrive in the future. So there are several options, and I just will go quickly over them. First, you can learn as much as possible about us and what we are trying to do, and it's the most efficient way to start understanding how you could help. So we have a YouTube channel with all these salons that are recorded. You can also all the events, all the conference, lecture, etc. Connect with us, of course, on Facebook, LinkedIn, and you will get all the posts, all the information. And of course, you can donate. This is the most direct way and easy way to advance our mission. For that, just go on our website. You can donate directly through PayPal or crypto, Zcash, Bitcoin, Ethereum, anything you want. You can also really some easy way is Amazon Smile. I don't know if you know that. You can donate a percentage of each one of your purchase to Foresight Institute. You can also. Am I forgetting anything?
There's a lot of things.
Yeah, there's so many ways.
You can also write us too an email if you want to.
Yes, I think that's an important one. We are really. This is first and foremost a community, and I think this was really something we felt tonight with these questions, and it feels really at home, and we are all sharing this desire to create positive futures. So we are really open to suggestions. Just tell us what you want to do and what are your ideas, and for that you can send an email at foresight@foresight.org. So that's easy, and I think that's all. If I forget anything, just go on foresight.org, take action webpage, and you have all the information to help us. Thank you.
Thanks, guys.
If you want a tour of the